It says electrons and light. Prometheus, thief of light, giver of light, bound by the gods, must have been a book. So it's a parallel between the Prometheus, the legend, and a book. The learning goals are that you understand the interaction between the electromagnetic spectrum and the atom, that you understand the information that can be obtained from the various types of spectroscopy, that you distinguish between classical and quantum models of the atom. You should be familiar with that already. You should be able to assign quantum numbers and fill electron orbitals. You should have a general understanding of that, but maybe not quite to the level that we need. And you should be able to understand the relationship between electron configuration and physical and chemical properties. So the first thing that you should be familiar with, both from physics and from first year chemistry, is the fact that there is the electromagnetic spectrum. It consists of all frequencies of light, starting from radio and actually going all the way up to gamma. Okay? The speed of all electromagnetic radiation is 3 times 10 to the 8th meters per second, sometimes commonly referred to as the speed of light, but it actually refers to the speed of all electromagnetic waves. So here you see that the electromagnetic spectrum consists of radio, micro, infrared, visible, UV, X, and gamma. Okay, those are the different divisions of the electromagnetic spectrum. The first one is radio. Radio tend to be very low frequency, low energy, high wavelength. So the radio wavelengths tend to be very, very big. Okay, they don't have a high frequency. They're used primarily to transfer information between two things. So we think of radio signals. Microwaves are slightly higher in energy, slightly higher frequency, slightly smaller in wavelength. So you see this is the general pattern. Cell phones and microwaves actually operate at microwave frequencies, which makes sense. That's why they're called microwaves. Next you have infrared. Once again, we have slightly higher energy than microwave, slightly higher frequency than microwave, and so on. Next we have visible light. Visible light is the only part of the electromagnetic spectrum that you can see, and it's in the middle in terms of frequency, energy, and wavelength. Next we have ultraviolet. Ultraviolet is high frequency, high energy, low wavelength. One of the interesting things about ultraviolet is the first one that can actually really penetrate the skin and cause sunburn. It can be used to sterilize instruments because it actually causes cell mutation in different bacteria. So it is actually the first one that really is dangerous. Next we come to X-rays. X-rays are higher frequency, higher energy. They can actually penetrate through all the layers of skin and actually not quite through the bones, but that's how you create an image of the bone. And then finally you have gamma rays. Gamma rays are the highest energy, highest frequency, lowest wavelength. So where we said radio was this, gamma is this. Okay, a whole bunch of waves in a very, very small segment. Okay, the only real use that we have for gamma rays is we do use it in radiation therapy to treat cancer. Now, you should be familiar with this equation already. This is the equation that governs all electromagnetic radiation. It says that C equals lambda V. Now, in the first year chemistry, we tend to refer to this as F for frequency. In AP, they tend to refer to it as V, and a lot of times it has like a little symbol over there. It's called a tilde, I think, that's over the V, and that actually represents the frequency. And it's just the difference between chemistry and physics. Physics will oftentimes call it F for frequency, whereas we call it a V. Okay, so you should be familiar with those variables: speed of light in a vacuum, wavelength, all those sorts of things. Next, we say the sun emits all different forms of EM radiation towards Earth. Which segment of EM spectrum will reach Earth first? And if you were to look at this, this is a common question. A lot of times I gave it to a first year chemistry is the sun emits a gamma pulse. Can you have a satellite that warns and puts a shield around Earth in time? And the answer is no. All forms of the electromagnetic spectrum travel at the same speed, so it doesn't matter if you have radio signals or gamma rays. They all travel at the same 3 times 10 to the 8th. Next it says what is the wavelength of red light in nanometers, and it gives you the equation 4 times 10 to the 14th. Okay, so the first thing you need to recognize is that we're talking about part of the electromagnetic spectrum. So you have C equals lambda, I wrote it as F, should be really C equals lambda V. You have C is 3 times 10 to the 8th meters per second, and you have V, which is 4 times 10 to the 14th, which is hertz. And this is an example of a calculation that could be done in the multiple choice part of the AP chemistry exam. It's one that you don't actually require a calculator in order to do. And so let me kind of explain that. You're actually looking for the wavelength, and if you set this up, you would say that C equals lambda V, or 3 times 10 to the 8th equals 4 times 10 to the 14th V, or excuse me, lambda. If you do that lambda At that point, you would take both sides and you would divide it by 4 times 10 to the 14th. When you do that, you cross this out and you end up with 7.5. The reason why it's 7.5 is 3 divided by 4 is 0.75. But we need to put it in scientific notation, so that's why I reported it as 7.5. The next thing that you do is you're dividing these, so you actually subtract. So whenever you take 10 to the 8th divided by 10 to the 14th, you actually get 10 to the negative 6th. But remember, this was originally 0.75, so the fact that I moved it over 1, this needs to move over 1 as well, and you get 7.5 times 10 to the minus 7th meters. Now on the AP exam, there'll be multiple choice. And it'll be one of those things where you can quickly see that 3 divided by 4 is 7.5, and you would be able to eliminate all the ones that were 4 divided by 3 that were numbers other than 7.5. So it's one of those things that's a trick that you can use. It's a math problem, but you should be able to solve it without a calculator. So the question we need to ask ourselves is, what is light? And the most common definition of light is that light is a wave. And there is some experimental evidence to back that up, and that's Young's experiment that provided evidence that light is a wave. Now, one of the things that's really important in AP is you need to understand the experimental evidence, because a lot of times they will give you a question that gives you evidence and ask you what the result is. Well, it turns out when they put a single light source, okay, this is a monochromatic light source, which means it's all yellow light, and they cut 2 slits in a piece of paper, and they shone this light on the paper, and they allowed the light to interact. So you have a light source here, and you have a light source here. Now you know it's identical light because it all came from the same light bulb. Well, if you have these 2 sources right here, what you would expect to see if light was not a wave is you would expect to see bright and fading and bright and fading for these 2 different slits, like a flashlight. When you shine it on the wall, there's a bright spot and then there's fading spots. But the interesting thing they found out was that when you did it, you actually got this, it's called an interference pattern. So you have a bright spot in the middle, and then you have a dark spot, and it's the dark spot that makes the difference. It's like, well, wait a second. How can I have a dark spot? And you say, well, it's where the light fades away. And that's true, but then you have another brighter spot on the other side. The only way that that could actually happen is if the light waves were interfering with each other. In this case, it would produce a bright spot. And the reason why it would produce a bright spot is if you have a peak and a peak overlap, those waves add together and get larger. And also, likewise, these dark spots are caused by the fact when you have a light wave overlap with a light wave, these 2 overlap and they cancel each other out. The absence of light produces the dark spot. So this is Young's experiment. It proved that, or gave evidence, it supported the idea that light was a wave. So light was generally considered a wave until the photoelectric effect experiment. Now this is an experiment that stumped scientists for a long time, and actually Albert Einstein in 1905, he was the one who actually explained this phenomenon. In 1905, Albert Einstein wrote 3 papers. They finished basically first, second, and third in the Nobel Prize competition. So what it is if you take a light and you shine it on what's called a photoemissive surface. So in other words, if you take light and shine it on here, electrons can come out the other end. When electrons come out the other end, you can detect that current coming through the battery, and usually it hooks up to a light bulb or something along those lines. They didn't have light bulbs back then, but they had ways of measuring electrical current. The really interesting thing about this is if you use red light, nothing happens. But if you use violet light, then all of a sudden this thing lights up. And so that's really, really strange. You ask yourself, okay, well, how can that possibly be the case? And the answer is this. If light was a wave, these waves would just build up and build up and build up until an electron came off. But if you don't think of light as a wave, if you think of light as a particle, if a particle comes in and hits another particle, this particle is not going to move unless this one comes in and hits it hard enough. Think about if you play pool. If you hit the cue ball and you barely touch the cue ball, it's not going to make whatever ball this is, the 8 ball, move. But if you hit this thing fast enough, with enough energy, with enough velocity, it is going to take this thing and knock it loose, and it can go around the rest of the circuit. So this gave evidence that light was a particle. So we have what now is what we call wave-particle duality, that light has behaviors that are waves and light has behaviors that are particles. And scientists can use this wave-particle duality to kind of design experiments in such a way that would produce the most beneficial results for whatever they're trying to observe. So what is electromagnetic radiation? electromagnetic radiation, light, is produced from falling electrons. So what we have here is electrons can move up and down these orbitals. Now you learned that in first year chemistry. Whenever an electron moves up, it actually gains energy. Okay, it's called the excited state at that point. Electrons generally don't like to be in the excited state, so what happens is those electrons fall back down. But in order for conservation of energy to be maintained, whenever this thing loses energy, energy has to be emitted, and is emitted in the form of a photon of light, or you can think of it as a wave of light, however you want to think of it. Now what this means is that you can only have light or electromagnetic radiation produced when these two orbitals have a specific distance. So in other words, I can't produce light from here to here because the electron can't be here. It can't be there. So what this results in is every atom has a unique color pattern that's produced as a result of the distance between the orbitals. So this right here is Planck's equation, and it used this idea, the fact that the energy and the frequency of radiation, so once again this should be V. Okay, it just depends on the textbook really, but E equals HV should be the equation. And what you have is, this is the energy. This is the same energy that we've talked about quite a bit, energy in joules. This H value is called Planck's constant. Okay, and it is 6.626 times 10 to the minus 34th. Okay, that is the value of Planck's constant. It is a constant, like the name implies, so it doesn't change values no matter what. And then finally you have the frequency, and frequency we've talked about is the number of cycles per second. So now, what is the total energy of 1500 yellow photons if the wavelength of the photons is 580 nanometers? So this is kind of a tricky question, because really what I want to know is I want to know what the energy is. And this equation right here that I have is the energy of a single photon. This is saying if I have one photon, this is what it would be. So I need to do a couple of things to modify this equation to make it work for me. Now, if I have 10 photons, all with an energy of 1 joule, I could just take 1 and multiply it by 10, and I would have the amount of energy that's in 10 photons. So what I'm going to do right here is I'm going to modify this equation by putting an n there. The n just refers to the number of photons that are present. Now whenever I do that, I really want to put like a little subscript n right there. What that indicates is that it's the energy of a certain number of photons, not just the energy per photon. So now I am trying to find the energy, and you can actually write it as energy 1500. That's what a lot of times what you'll see in a textbook, and that's what you're trying to solve for. Now another thing that you'll see is, although I do have Planck's constant, which is in fact a constant, I don't actually have the frequency. So this work allows you to, you have to use your prior knowledge that we learned in the previous equation, and you have to substitute in the equation C equals lambda V. Okay, so I don't have V. So what I can do is I can write an expression for V that is V equals C over lambda. And what I can do is I can then substitute that in there, and my equation now becomes E equals N HC over lambda. So there's a lot of algebra that's involved here, but it's the basic idea that I would solve for the frequency first, and then use the frequency to solve for the energy. So I do know Planck's constant is 6.626 times 10 to the minus 34th. I do know that the speed of light is 3 times 10 to the 8th. I also know that the n value in this particular problem is 1500, and that would allow me to, and the wavelength would be 580, but that's in nanometers, so I'd have to multiply it by 10 to the minus 9th, because that's the conversion between nanometers and meters. And I know that's not in scientific notation now, but you can fix that whenever you put it in your calculator. So now at this point you would plug it into the calculator. This is not a type of question you would see on the multiple choice part of an AP exam. It is not a calculation that is easy for you to solve, or easy for you to manipulate, or easy for you to simplify in your head. So at this point you would use a calculator, you would go ahead and solve it, and you should be able to do that. Same thing here, we have how many red photons would it take to equal the energy of 10,000 violet photons. And so we have another situation in which we're trying to have the energies equal each other. So I want the energy of the red to equal the energy of the violet. And so what I'm going to do here is I've actually got it easy for the red photons. I can actually use the equation HV because I have the V. With the violet photons, it's a little bit more difficult because, and actually we have to solve for N right there, so N red. And this right here is going to be N purple. How many purple photons? And I can't use this HV again. I have to use the HC over lambda because I was given the wavelength. Now, one of the things that you can look at is there are some ways that you can simplify this before you actually get involved. You can actually cancel out Planck's constant because it's on both sides. So at this point, you would have the number of red photons is equal to 10,000, and then you would have your C. Notice how I didn't put the H value in there. And then you would have to divide that by the lambda, which is going to be 430 times 10 to the minus ninth. And then you would also have to include the frequency of the red photons, which is 4 times 10 to the 14th. Now, this is one that could potentially be on an AP exam on the multiple choice. I don't think it would be. And the reason why I don't think it would be is because of this 430. But if that was a whole number, like a 2 or something like that, you would see 3 divided by 4 and then 1, and you could simplify it. But this type of question will not be on the multiple choice portion of the exam. There are three types of spectrum we need to talk about. The first one is a continuous spectrum, and that is something where a light source produces all colors of light. An example of a continuous spectrum is the sun. The sun contains many different elements that actually produce all of the colors of the rainbow. So you see a continuous spectrum there. What you have here is called an emission spectrum. Whenever you take an atom and you excite the electrons to the next level, and then you allow them to fall back down, what happens is it produces a single color of light for this transition. There's a certain energy difference between those two. So whenever you produce that certain color of light, it shows up on what's called an emission spectrum. And that's the light that is produced as the electron falls from here to here. So if you see, the emission spectrum tells you how many orbitals or the orbital transition energy between the orbitals. Now if you look, the absorption spectrum is the exact same thing as the emission spectrum except this. What happens in an emission spectrum is you have this same element, but what you're doing is you're exposing this element to all frequencies of light. So you're taking this thing and you're shooting all the light you can at this atom. But what happens is the atom can only absorb energy that is equal to this transition level. So what happens is that energy of that frequency is absorbed and makes the electron go up to a higher level. So it produces a gap whenever you read the spectrum. So the emission spectrum and the absorption spectrum show the exact same information, just in a different way. You should be able to draw the emission spectrum given the absorption, or absorption if you were given the emission. So here are some emission lines. So you see the emission lines for helium, hydrogen, mercury, neon, and sodium. So what you can do is you can actually use these emission lines to identify an unknown element if you were given the standards. So if I were to give you a standard set of emission lines like this and then give you another spectra, you should be able to tell me which elements are present. In order for an element to be present, all of the spectral lines that are present in the spectrum must be present in the sample. So for example, if you had an unknown spectra that had this line and this line and this line, but not these two, it's not helium. It's got to be something else that has those same or similar lines. In order for that element to be present, all spectral lines must be present. So the Rydberg equation was actually used to explain the spectral lines of hydrogen. So there were several spectral lines of hydrogen, and what they did is they actually came up with a mathematical relationship. And all they did was they actually modeled it. They took the different information where people had observed spectral lines, and they kept messing with the formula between the two until finally they came up with this value right here. So this equation right here represents the spectral lines of hydrogen for a very, very specific part of the spectrum. But they do not represent all the spectral lines of hydrogen. Instead, there are some of the spectral lines of hydrogen that are missing, and those were actually from the Balmer series and the Lyman series. Now, the reason why this doesn't represent all of the spectral lines is because of this. If you have a hydrogen, we generally only think of hydrogen as having an electron in the 1 orbital, and then if it gets to the excited state, the electron goes to the 2 orbital. But there are actually many, many more orbitals for hydrogen. In fact, there's an infinite number of orbitals. So what you have here is the first one is only representing transitions between the first and the second state. Really, everything to the ground state. So 2 to the ground state, 3 to the ground state, 4 to the ground state, infinity to the ground state. But the Balmer series and the Lyman series actually developed a second equation that's very similar, and that will actually show the orbital transition to the second and to the third one. So 4 to 3, 5 to 3, or 4 to 2, 5 to 2. So realize that these spectral lines are produced by all of these potential electron orbitals. The Bohr model of the atom is the one that actually allows us to reference these spectral lines. The Bohr model of the atom is the one that we say that electrons orbit the nucleus, that the electrons have to be at a specific distance. That distance is called an orbital. Absorbing energy makes the electrons move higher, emitting energy makes the electrons move lower. So just as kind of an extension, we talked about there being an infinite number of orbitals. Well, if you look here, as you go from 1, if this is the first orbital, 1 over 1 squared, that's 1, right? So if this term is 1, if this is infinity, well, if you know that 1 over infinity simplifies to 0. So the absolute energy that you can get there is 1 minus 0 times this. Now, if you exceed that value, if you are at an energy that is greater than the one that takes it to the infinite orbital, what you have is you are removing the electron, and that's actually what we call ionization. Talked about the Bohr model. This right here is the energy levels once again. It says light is created by electrons falling from orbits. And here you see the Lyman series are the transitions to the first orbital. You see the Balmer series, which are the transitions to the second orbital. So those are those series that you have here. Now these will actually simplify to this equation right here. Now this equation right here will actually tell you that the energy of a particular electron is related to H, which you know is the Planck's constant, C, which you know is the speed of light. This right here is called the Rydberg constant, and then this right here is the orbital that you're looking at. Now all three of these constants are represented on your AP formula chart. So now we have to start example C1. We can start to look at the calculations for the formulas we just showed. It says, what is the energy of an electron in the third energy level? Actually, a better question for this is, what is the energy required to remove an electron from the third energy level? Because that's what we're doing when we're looking at these equations. So if you look right here, we know that we have the third energy level, and we know that we want to use the equation E equals minus Hc RH divided by N squared. Now this is the equation for the energy required to remove an electron, hence the negative sign because you're actually pulling the electron away. And what you have right here is this is the H value. It's the same H value we've been working with, which is 6.626 times 10 to the minus 34th. This C value is the same C value we've been working with, 3 times 10 to the 8th. This RH value, the Rydberg constant for hydrogen, and really hydrogen is all we'll deal with right here, is 1.097 times 10 to the 7th, and you could look that up on your AP chart. So you're going to take these numbers and you're going to multiply all of them together, and then you're going to divide by the N squared value. So in this case, our N value is going to be 3, so 3 squared, which is 9. At this point, you would put it in a calculator, and you should be able to come up with a reasonable number. You should realize it's going to be a pretty small number. The reason why is you still have this 10 to the 7th and 10 to the 8th, those are large, but then whenever you take into account that negative 34, you're going to end up with a relatively small number. I believe it ends up being something like 2.43 times 10 to the negative 19th joules. And you say, well, that's a really small amount of energy to ionize an atom. And you say, well, yes, but that's the amount of energy required to ionize a single atom. And we usually talk about moles of atoms, so that's actually quite a lot of energy. The next one says, an electron transition from the fifth energy state in a Lyman series transition. What is the wavelength of the photon emitted? So this is one of those questions in which you're trying to find the wavelength. So we're going to have to use the 1 over lambda equals RH. And then we have 1 over n squared minus 1 over n squared. Okay, because this is dealing with what's an electron transition. So the other formula we were using it was talking about an ionization. Now, actually, the two formulas tend to go hand in hand, but really what it is whenever you ionize something, remember that's infinity, and that crosses out to zero. So that's why we separate the two formulas. One is the ionization formula, and this is the electron transition. And so at this point, we need to know that we need to transition it between two energy levels. Now, it is a fifth energy level, and then it's a Lyman series transition. So the fact that it's a Lyman tells me what the other energy level is. And if you remember your previous diagram, N is 1 in a Lyman transition. So we can show you right here. You have a Lyman series. Lyman series are always the ones that go to the first energy level. Okay, so then we can say, okay, if I have a Lyman series transition, that means I'm going to go 1 over 1 squared minus 1 over 5 squared. Okay, so 1 squared, 5 squared, and then you have to multiply it by the Rydberg constant, which is 1.097 times 10 to the 7th. Okay, once you've done that, you have that equals 1 over lambda. So in order to get the lambda value, you'll just go ahead and take the minus 1 of both sides, and you'll get lambda is, and I'll leave that for you to solve. You should be able to solve that and tell me what it is in class when you get back. Next, we have the limitations of the Bohr model. We know that the Bohr model of the atom is not the greatest model of the atom. It works phenomenally well for hydrogen, and it does. But hydrogen is very unique in that it is a one electron atom. It's a one electron system. As soon as you add a second electron in here, so if you have one electron here, as soon as you add a second electron anywhere, the Bohr model falls apart. So it doesn't even work for helium, let alone uranium or anything like that. And the reason for that is the Bohr model of the atom can explain the interaction between the two electrons. Now, the Bohr model is a phenomenally accurate model, but it's not perfect. So oftentimes what we do is we approximate things with the Bohr model of the atom to get very close, and then we have to use other models in order to get to a more accurate value. So the next most So we have the energy state. The lower the energy state of an atom, the more stable an atom is. We've talked about that. So you should know the difference between an excited and a ground state.